Hello, everyone. How we doing? Yeah, woo! All right, thank you for coming to Building WebAssembly, or like it's 2011. We're so happy to have you all here. My name is David Justice, and I am joined here.
Hi, I'm Terence.
So I am a CNCF Wasm Working Group co-chair, and also a employee at Microsoft. Terence, who are you?
I work at Heroku. I'm an architect over there, and I got to co-create Buildpacks 2 times, so that's been fun.
That's awesome. I'm so happy to be on stage with you.
Yeah, so kind of going through the agenda real quick in case folks get lost. We're going to do a quick intro on Wasm, the component model, kind of a quick refresher, take a tour through Buildpacks for those who aren't familiar and how that helps our problems here, and then bring them together and then kind of look where we're going to head in the future. Let's kick it off, David.
Awesome. Thank you so much, Terence. All right. How many in here have built a WebAssembly module? Yeah? How many in here have built a WebAssembly component? Awesome. How many people have fused 2 components together? Oh my goodness, there's more than I expected. That's actually pretty amazing. Okay, so we're going to do a little bit of that today. I'm going to give a little background first, so this might be a little bit of a refresher for folks that know it, but hey, let's jump into it. Okay, cool. So what is WebAssembly? WebAssembly is an application binary format that provides us portability, sandboxing, and efficiency and performance. It's also really nice because it kind of allows us to do it from many different languages. So if we had Go, JavaScript, .NET, Java even, we can take all those and hit that intermediary binary format and then be able to execute it on the server, on the edge, like anywhere in your browser. This is really cool. This is kind of the promise of run once, write once, run anywhere, but it's really low level. So it's so low level that we need to create some kind of a wrapper around it, because that low level interface is really just integers. So we got pointers. We got pointers at the beginning of like a string and the length. And that's pretty much how you represent all high-level types. So we introduced this idea of this component model. So you want to think of the component model kind of like your .proto files. Who out here likes to write the binary serialization for their proto endpoint, or their gRPC endpoints? Anybody? Come on, isn't that fun? It's not? Is it not actually dangerous and terribly tedious to write a binary serialization format? Yeah, it's horrible. And to do that over and over again for every single endpoint, it'd be awful. So the idea is this component model provides us this outer wrapper around core Wasm modules that handles this for us. It's kind of like our proto wrapper. Let's go next one. This is actually what it looks like. So this is actually like the most readable version of a proto file I think I've ever seen. It actually looks like a language that you're describing an interface in. So this is called WIT. This is the WebAssembly interface types. And this is the equivalent to proto, except for WebAssembly. So we can describe high-level structures. We can describe records. We can describe resources. We can describe functions. We can describe worlds. And in fact, it's actually worlds. Like worlds is a key term. So we'll dig into that a little bit. But this is how we describe how we put 2 components together and what interface they expect from each other. It's really kind of fun. All right. We would not be right in Britain without Mary Berry. So, if anybody out there is a big fan of the Great British Baking Show, I know I am, we're gonna go make a layer cake today. And if you look at it, Mary Berry makes this stuff look super simple. And our layer cake is kind of look like the thing on the right-hand side. Your left, my right. So you can see in the center of it, we have our JavaScript language, the code that we've written in JavaScript, and below it, we have this like little block called Starling Monkey. Starling Monkey is a derivation of Spider Monkey and gives us some really nice runtime characteristics specifically for running really, really low latency starts. So this is really nice if you were running like a function as a service kind of thing. And then we're going to wrap it with a WIT interface, make it nice, and then run it within a WASI compatible Wasm runtime. We're going to make that really awesome layered cake that Mary's showing. And she looks so happy doing it. I think we're going to be happy at the end too. All right. we're also going to do it with Go. We're going to marry Go and JavaScript together. It's going to be like our trifle. You ever see her make trifles? It's like layer, 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 layer. Well, it throws a lot of different flavors in there. We're going to throw in Go and JavaScript. This is how we would normally go about this. This is like the simple case. You know, you go generate, go build, and out pops, whoop, application. Voila, c'est magnifique. Now, you don't get the same experience with WebAssembly. Now, what do you get? This is a really complicated recipe. Oh boy. I don't even know what half these ingredients are, let alone how to combine them. We start off with WKG. In fact, that's actually pronounced whackage. That is for fetching your WIT definitions from an exterior source, actually an OCI registry. And then my Go has turned into a tiny Go, which tiny Go is not quite Go, just like CGO is not Go. Node kind of stayed the same, NPM kind of stayed the same, but we've started to add more tools to it, like JCO. JCO is your JavaScript component tooling. It's got a bunch of different tools in there based on some standardized Rust tools, and we'll use it for a handful of things like actually making a component. And then afterwards, we have this thing called Whack. It is not Whack, it's actually pretty cool. It fuses components together based on interface structures from the WIT, and then fuses them together to create a final component of them put together. So what are you thinking? Oh my goodness. And it would probably turn out that sloppy too. It did for the first 5 times for me. So maybe you'll all do better. Hopefully after this talk you'll do better. So let's see, how are we gonna fix this? Terence, tell me how we can fix this.
So I'm going to take us back to 2011, and during this time, we kind of rewind time. This is actually a time period when I was working at Heroku at the time. I think that makes me kind of old there. And so we were actually so Heroku was a Ruby-only platform. We were on this process of making this polyglot platform. At the heart of that transformation was this concept called Buildpacks. And what Buildpacks let us do is it allowed us to extract all the language-specific bits from the build process and let Heroku be this language-agnostic platform, right? And so a Buildpack would automatically detect what kind of application you had. Was it a Java, Ruby, Node application? Figure out what tools that you need to run, as well as kind of optimize your application for peak performance. So you, as the customer of this thing, could kind of just focus on building your application. Sounds great, right? And as part of that, we actually open source Buildpacks during that time period. And you know, there was adoption from various companies and people in the space. One of the kind of prominent players was Pivotal, as they're working on Cloud Foundry. And they actually kind of took our Buildpacks, and then as the fork, they actually like made a separate API, had a totally separate ecosystem. And so we were actually on these like diverging ecosystems. And in 2018, we got together and created Cloud Native Buildpacks. So we wanted to do kind of 2 essential things. We wanted to bring our ecosystems together, because it kind of sucked that they were separate and you couldn't have Buildpacks that were necessarily compatible with both. And there's this whole like Docker container thing that was happening at that time. And so we also wanted to, instead of have a bunch of proprietary output and artifacts, actually create things that basically worked in that ecosystem, played around with it. And today we're a CNCF incubation project, and we actually just submitted our graduation application earlier this year. So hoping that goes through, but we'll see how long that takes. And so, you know, Buildpacks, we're now cloud native Buildpacks, kind of what's different. So it's still source code centric, focused on application. And what you get out is, instead of this proprietary artifact, you're going to get an OCI image, you know, things that you can use with Docker, things that you can put in an OCI registry, right? And what you get is this well-structured application that has layers that map logically to your application itself. And the Buildpacks themselves are these composable units that encapsulate a specific technology, right? And when I talk about technology, I mean stuff like a Java, Node.js, you know, like those kind of things, a Ruby, Python, things that you'd want to kind of standardize how things should be built, right? And the other kind of nice benefit is that they can be composed together and used so they're executed on a particular build pack platform, but you can have a bunch of build packs that are executed and working together. And so as the end result of that, if you're an application developer, right, one of the things that you don't have to do by using Buildpacks is have to artisanally handcraft like that Docker file where you're copying and pasting lines and trying to make this production thing work and fit all the things you want, right? You can leverage these Buildpacks and they'll put all the things that you need to have it run and have this image that you can use for your application. With the Buildpacks themselves, they allow you to standardize how those applications are built. So inside of a company, you can have Java built the same way across your entire company. So you don't have these individual Docker files for every single application in your company, right? That are mostly doing the same things, but you get these kind of snowflakes throughout your company. And this essentially, and I was mentioning that Buildpacks are composable, right? And so what that allows platform operators to do is you can actually decrease the number of base images that you need to run, right? So you don't have, it's very common, right, to have like my base image like a rel 9, right? It's like my rel 9 plus this specific version of Java. And then if I want the next version of Java, that's a totally different base image. So that operation team's like running those two things. And God forbid if I have a Node.js image I have to run, and then the combination of those things, right? The combinatorics become very high because you have to maintain all these things so your application developers can use them, right? And so with Buildpacks, you can essentially have a single rel 9 base image and then rely on Buildpacks to essentially do that composition for you, getting you essentially all that organizational efficiency that you want for that standardization. And the easiest way to get started is to use our local CLI platform called Pack. You can install it through Homebrew. It's part of, the standard. We have Linux packaging as well through Debs, Arch, etc. And you just get that installed and you run Pack build and the name of your image. And so kind of digging in on what happens with a Pack build. So looking at Pack, it's going to take two major inputs besides what you want to call your image. You're going to have the application source code, and then we have this concept called the builder image. And so the builder image is composed of a few things. You're going to have those build packs that you want to vendor in and potentially run, and you're going to have what we call the lifecycle. So that's maintained by the Cloud Native Buildpacks project. And it's essentially the spec compliant thing that essentially runs a build pack through, well, the lifecycle of what a build pack should do. And then it's going to sit on top of a build image. And so this is going to be kind of that build environment that you're going to run your build in. And there's also a reference to the run image, because on the kind of output of this side, we're going to put all the layers that are constructed as part of that build pack on top of that run image. And in our example that we're going to go through in the demo today, we're using a Ubuntu build image, but our run image can be a distro-less image, right? It doesn't have to be the same thing, but it has to be a thing that you can actually build and have it actually execute in that environment, right? And so let's walk through what a build through Pack would look like, right? And so in this example, I'm just going to take a standard Node.js application. We're going to use Yarn in this case, kind of at the top. So the first thing that kicks off every single build pack build is the detect phase. So we need to figure out what build packs actually run, right? So you can include in your builder all these build packs, but not all of them have to run. And in this case, the first kind of grouping is that passes detection is going to be one that actually gets executed. In this case, that's going to be, we see that there's a package JSON, there's yarn.lock. You're going to want to run kind of that Node.js build pack and then a Yarn build pack to kind of do that setup and install. And they get to create a build plan. And so this allows build packs, talking about composition, to actually communicate and talk to each other, right? And so they can have information around like what is needed and things like that, and those get used as part of the detect to create this build pack plan. I'm going to skip through kind of the restore and analyze because that's not really used as part of the first build. So we're going to cut through to build, which is kind of the bulk and meat and potatoes of the build process, right? So this is where the build packs can actually like install your node runtime, run your yarn install, kind of set up all the things to actually get a running application. And they're going to put into specific directories, one per layer. And then all that gets packaged up in the export phase into an OCI image, as well as any of the metadata specific to that layer, so we can decide if we actually need to upload that layer on a subsequent build. And finally, layers can be marked if they should be cached or not, so we can use them in the next build to decide, I don't have to install all my dependencies again, right? I can reuse layers, and I can even modify them between builds. So this is kind of what, if we're to blow this out by the phases on the left, or my left, I guess your right, and kind of the OCI image and the cache image, right? So these are the things we're going to be uploading to the registry. And I was mentioning how the layers are mapped logically to your application. And you can see in that OCI image, right? Like we have a layer specifically to Node modules, and it's not just like some random command that we ran in a Docker file. Like the Buildpack author gets to really set like what goes in each particular layer. And if we go through a second build, we're going to do detect. Not going to talk much about it because it's going to look the same as the first build. So now we're going to actually get a restore. So we're going to go through and restore all the cache layers, kind of that bottom image from before, on what we need, right? So like everything we can use on the second build, if it's available, we're going to restore it on disk so we can use it on this next build. And the next parts we're going to run analyze. So we need to know metadata about the specific layers to decide, do I need to make any changes? Do I need to actually upload it, right? Like, should I bust this cache? What can I do with that? And so in this example, we're going to be updating the Node.js runtime. And so in this particular case, I need to know information about what the version of Node is that was there before and what I'm doing with the new one, right? And so in this phase, we're just pulling that configuration from that previous build. And then we're going to do the build. We're going to go look at that thing, install that new version of the Node.js runtime. It's a patch version, so I don't need to update the Node modules layer at all because it's API compatible. And so eventually we can export that after the build, and we only actually have to upload the specific layers that have changed. So all the things that haven't changed, like that Node modules directory, your application directory, pieces that don't, like we can keep those same, export them, update that, all the metadata per the layers, and here we go, right? Like we just update those specific things. And finally, we cache all that stuff together and for that next build so we can be equally as efficient. And so in this case, we're just uploading that one Node engine layer that we uploaded in the OCI image to be there for caching. And now David's going to walk us through how we can apply kind of all that stuff into Wasm.
Thanks so much, Terence. And I got to say, Heroku's always been an inspiration for me as far as dev experience goes. And I think we have such a huge opportunity in the Wasm space to offer a great dev experience. And we can start with the tools that we have available to us in the CNCF. We have some great tools available, and we can help each other to be more successful. So, Mary is super excited about that one-liner right there, because we took all of that knowledge that Terence just dropped on us, and we applied it to WebAssembly. We went through and we built out those build packs there. Wasm Tools goes and installs all those gnarly tools that you saw in that recipe. Wasm Time Engine brings us that Wasm Time runtime that we need to run that WebAssembly component. Then we piggybacked on a little bit of a Heroku build pack love, bringing in some Node.js. We also tried that with Go. We had a little bit of trouble, so we backed that one out and just wrote a Go build pack, which is not any problem with the Heroku build pack, more just the nature of our project. Then we have the WAC Analyzer, and the WAC Analyzer goes through and takes a look at your project to understand if it's a mono repo filled with multiple components. The Wasm Node.js understands how to deal with a mono repo with a Node project a little bit further down the tree. And then same thing with Golang, almost the same reason. And then we have the WAC Composer. And the WAC Composer is kind of interesting. So it goes through the mono repo, figures out like what projects are where, and then informs later during the build phase, during the build phase, goes through and says, all right, cool. I'm going to go find all the JS projects, build those, collect the components from them, do that same with Go, collect the components from them, put them in a cached layer, and then we have the Wasm Finalizer. And it's kind of the rug that pulls all the room together, right? So the Wasm Finalizer gives us a clean image at the end, because all we actually need, we don't need any source code. Normally, what would happen in the last step is that source code stays in the working directory. We just take the WebAssembly components, or maybe even just that one component that we've composed together, and that is what we keep in the final build. So we end up with a container image that contains Wasm time and your optimized final runtime component. And that leads us to Mary being very happy. what does our component structure look like? So this is actually relatively simple, right? But I wanted to illustrate the ability to use WebAssembly components to mimic what you would normally do across a network boundary. So normally in your WebAssembly, your microservice infrastructure, you're going to have a network boundary between your services, right? You're going to have your gRPC endpoints. You're going to have to, write the code for those, make sure they're insulated, and they have to be able to talk together. They have to be able to address each other. They have to be able to load balance. You got a lot of difficulties there. So what if we could take microservices, smash them together? So that's actually what we're doing here. So we have a JavaScript front end that exposes a few HTTP endpoints. And then we have a Golang backend service that talks to OpenAI and gives us some chat completion. And then, does the really, really stupid simple thing of adding numbers together. All right, so here are WIT worlds. You'll see example.service and example.server. Example.server is our HTTP front end. The world exports a incoming HTTP handler, but it imports adder, chat, and the domain types that are described. On the other hand, we have our backend service, example service, and it includes WASI CLI, which is a standardized interface for running CLI applications, exports a CLI runtime, or CLI run interface, which is a run command for the CLI. Ignore those two because they were actually really just used for debugging to allow me to take that component and rather than actually compose it together with the JavaScript, run it independently as a CLI application so I could test it independently from the composition product. Finally, you'll see the include of the domain service. That means I'm going to pull in all those things in that WIT below, and then whatever that WIT below defines, for example, world service, which exports adder and chat, that means I'm going to then export those things. I kind of inherit those. And then I'm also going to import an outgoing HTTP handler because I'm going to interact with the OpenAPI library, or OpenAPI interface, HTTP interface. All right, so here is the demo. And this is actually an example of these build packs running on this mono repo. So, oh
sorry.
Goodness gracious.
Sorry.
oh gosh, okay. Here we go. Sorry, technical difficulties, folks. All right, I think we're good now. Okay, you'll see here's pack build, Wasm compose, the builder that we built, and the path in the mono repo. You'll get a link to the repo at the end. You all can go and play with the code. And you'll see that we kicked this off. And as Terence was saying before, it's going through the analyze and detecting phases. I actually sped it up just a little bit. And this is actually the second build. So it's run restore. You can see it's building the node, running the WAC analyzer, eventually getting to the go build. So while this was building, we ran in some technical difficulties that I am going to be delighted to share. And then also I'm going to expect a little bit out of you all because we're going to have some work to do as a community. And I'd love to get people excited about doing that. Oh my goodness, we got an image. Okay, fantastic. Now we're going to run that. We got our OpenAPI key in the environment. And if I could type faster and better, it would be great, but...
You didn't speed that part up.
No, sadly not. But it will be quick, I promise. So we're just going to say hello. We have the hello endpoint. Silly simple. Let's add a couple numbers together. Honestly, these are like the examples that you see in the WebAssembly community. We need such better examples than just like add two numbers together and, give me Fibonacci. So here we're actually going to use the OpenAPI endpoint for chat completion. And as you can see, that's the prompt. It actually goes out to OpenAI, makes a call, translates that back through Go into JavaScript, and you get the capital of England is London. And there you can see the actual code base. Again, that's out on GitHub. You're welcome to go take a look at it. We have lots of work to do still on it, but we've come pretty far. It's actually really exciting.
Oh no. I'll get back. There we go. Wait.
Just forward. Yes! Mary Berry is excited too. That was a little bit less, that was a little anticlimactic compared to.
Well, you know, slow typing. That's how we get there.
All right, so what do we learn about this? We learned that, Buildpacks, even though they're old and made by, wonderful people like this, they are extremely valuable. They are viable, and they can be applied to new ideas, new technologies, and they're fantastic. What we did learn that wasn't so great. Monorepos and structure for building WebAssembly components based in multiple components in one repository, possibly of different languages. We just don't have enough metadata to declaratively build these. We need to be able to inform some higher level builder all the data that we need to build that thing. So for example, the WAC compose takes in names of the worlds that you want to build with. That metadata just doesn't exist. You have to put it in by hand. There's no way to infer it based on the structure of the repo. However, we could think about opinionated ways to structure repos to make this easy. We don't have to have the hard time. We output in an OCI image. Well, that includes the WebAssembly runtime. There are projects in the CNCF like Run Wasm, which is a way to provide a runtime class that Containerd knows about in Kubernetes that can run components. So it embeds Wasm time or another WebAssembly runtime so that you don't have to embed the WebAssembly runtime into the image itself. Now, those components that get baked, those don't come out as WebAssembly images or OCI images. Those come out as OCI artifacts. They aren't actually, they're runnable artifacts. They're just not OCI images. They don't have all the stuff in there. They're missing the runtime. That's actually really good because that runtime's about 50 megs. That WebAssembly component included both the Go runtime and the JavaScript runtime and was 14 megs. Now, imagine if you built it with like Rust or something that doesn't have to include the runtime. You're talking about 2 megs. 2 megs for your OCI artifact. Think about how little network bandwidth you have to use pulling those down. It's incredible. It's a huge difference. Monorepos and Buildpacks. Now, the existing Buildpacks that I was using, and there may be others that do this better, but monorepos were a little bit tough. So maybe I needed Node. Well, Node has to see a package.json and a package.lock in the directory that it's running. And if it doesn't see that, then it bails and it says, hey, that's not a JavaScript project. Well, in fact, I needed your tooling, but it's somewhere further down the chain. There might be things we can do to help improve that experience. Maybe it's just different build packs. Maybe it's being able to rerun build packs on slightly different ways. And then we have library support. So we have the opportunity to, the OpenAI folks, they were so excited about hearing about using their library in Wasm, they wanted to go and implement that. So they put out a branch that worked for their library. Building in TinyGo, which it didn't work originally. I had to write all the code to go out and talk to HTTP. Okay, that's fair. Well, what if we wrapped a component interface around that library? It could be used by any language, anywhere that could run WebAssembly. That means you don't have to write libraries in 10 different languages. You write it once. You use it anywhere. Again, that promise that we heard. Okay, so the future. We have that opportunity to expand from just JavaScript and Go and do it for all the languages and have a build pack experience for a one-liner. That would be absolutely awesome, and I think it would help a lot of people. OCI artifacts. We have an opportunity to take these components, put them into OCI artifacts, enhance build packs to have that exporter, and just didn't have the time for that.
Yeah, it's coming.
Yeah. enhancing the model repo story for both Wasm and Buildpacks. And then let's imagine what it would be like if we started to build that library support. It starts with 1. And when you see that 1 and you use that 1, it calls you to make a second. It will start like wildfire. It will go around. It will make folks so much more productive. And you don't have to write the library 10 times, folks, or X number of times, whatever number of times your customers use those languages. It can be better. And we can do it together as a community. That's the point of why we're here.
That's all we had. Thanks, everyone. You can check out the repo right here that we've been working in for the last month or two. And yeah, I don't know if we have time for questions, but we'll be around.
Sorry, we were flying through those as fast as we could.
Yeah.
Thank you all for being such a great audience. You all are awesome.